Okay, we are live. Please tell me you can see me and you're coming over. Nobody's in this chat right now. There we go. Hello. Okay, I hope it's working this time and we can stay with it. There we go. People are coming over. Okay, you could see and hear me. I couldn't see you, so I'm glad you're back. Hi, Errol. Welcome to AP Physics. You're happy to lurk. Welcome to lurk. Okay, Yee. Okay, we got all kinds of people showing up now. Interesting. Okay, all righty. Now, if you're not in this class and you're hanging out, that's chill. But if you make any noise, I'm gonna boot you out of the chat. So don't do that. Okay, we got a bunch of people showing up. Good. Hi, Rhea, Sam, Justine, Octave, Yanis, Sammy's here. Good. We have at least half of you here. 1, 2, 3, 4, 5, 6, 7. Okay, that's pretty good. Okay, we'll just wait a couple minutes to see how things go, and then we'll kind of move on from there. Okay, hope you're all well. Nobody's sick. If you are sick, I hope you get better soon. Oh, we're down to 5 people there. It's interesting. Okay. Okay, while we're waiting for just a couple minutes to see if other people show up, I did message you guys that what I'm using, I'm going to do 1 or 2 free responses today. My plan is to use the 2012 released practice exam, and there are 2. At least the first question is really good, I think, on the free response, and the second question is also okay. Now, as we get ready now for the exam, as you know, and just to remind you of what's happening on that, a little bit, what they've told us is going to be 45 minutes. It's going to be taken by students at home. It's supposed to be somehow device independent. So if you use a laptop or a phone or a tablet, everything should work. And somehow you can then transmit it. We're guessing it's some kind of, maybe write it on paper and then take a picture or something like that. We really don't know, but we do know it's going to be free response and free response only. So in terms of where we're going now with the class, my plan is to focus on reviewing free response questions. We've had somewhat of a focus on multiple choice, and certainly that's still a good thing for you to practice your skills in terms of figuring out whether you know how to apply the physics. But in terms of specific preparation for the exam, probably free response is a better choice. Okay, so we've waited a little bit now, and my plan is now to actually look at free response question 1. Hi. Free response 1 on the 2012 practice exam, and to go from there. So I've got a board back here for us to work on, and I also have the questions printed out. And it looks like here's the question if you don't have it. There we go. That's the question we're going to work on to start with. Okay, so what do they tell us in the question? They tell us that they have 2 spherical shells. They're conducting shells. Okay, so the situation looks something like this. We have an outer shell, and pretend that's spherical. And we have an inner shell. So 2 shells. And the inside has a radius of 0.1 meters. The outside has a radius of 0.2 meters, okay? And they've charged these to, this one's minus 100 volts, and this is plus 100 volts. And they say in here that these things have charge on them, obviously, and they say that the two spheres voltages, and here's a specific wording, each potential is defined relative to the conventional reference point. So the conventional reference point, just a reminder, is that if we go really far away at infinity, right, potential is equal to 0. That's what the potential, the conventional reference point is for that. Okay. I just kind of just started in with this. I'm assuming this is a good thing to do. Are you guys okay with starting this way and doing this problem? I should probably ask you or something. I'm not sure. Is that cool? Are you guys still there? Yes. Okay. Thanks, Giannis. So you are there, and let's do this. Then we can maybe take some more time to talk about something else or otherwise. So let's take a look. Yep, you're good. Okay, good. All right, good. So and they tell us that there are charges on these, and we're going to label these creatively. On here is QO for outer charge. Okay, and then on the inner one, we're going to have QI on the inner sphere. Okay, wow, maybe colors would have been smart. All right. What's going on here? Come on. All right, okay, good. All right, so, all righty. Now, they're asking, first of all, they're looking for the algebra, for the electric field in between these two. So at a position in between, so somewhere here, at a radius r, they'd like to know the electric field. And well, that's pretty straightforward because I kind of really drew that in. It's all spherically symmetric, so we should have spherical symmetry. And just to clarify what that means, well, our outer surface has a positive potential. The inner surface has a negative potential. So it should have negative charge here, positive charge here. That makes sense. But either way, whatever the charge is on this surface here, right, it's the charge that's inside or dotted line Gaussian surface, which means that for part A, they're asking for E of R for 0.1 meters, smaller r, smaller 0.2 meters. So between the two spherical surfaces, okay? And if we do that dotted line there, all we need to do is apply Gauss's law that E dot dA is equal to Q inside divided by epsilon 0. So now just be careful. It's kind of a little bit of a trick here because that's the given equation on the equation sheet. So they're going to be unhappy with you if you just leave it like this, and they want to use the specific formulation that we have here. And what do we have? We don't have Qn, we have Qi, first of all. That's the first important thing. And the other thing here is that we're supposed to actually do this integral, but it's not a complicated integral because the electric field is constant on here, and it's going to be going directly out of there. So all we're going to do is, I'm going to write it over here, for pi r squared, where 4 pi r squared is the area times the electric field, and that's equal to qi over epsilon naught. Okay, I should have written it further over here because I'm a little bit short on space. So I'm going to just push this over here and then put our answer to part E right there and say E is equal to qi over 4 pi r squared epsilon naught. There we go. And we've got our full credit for part A. Okay, good. Okay, good. Let's take a look for qi, because qi is inside the dotted line. So the dotted black line here is our Gaussian surface, which is a spherical surface at radius r, which encloses the inner charge, this one, qi, but it does not include qo, the outer charge. That's from the center sphere's charge. So in the equation, it says qin, and qin means, actually it says technically not in, but enclosed. So when you're doing this, I think that's what it says. I don't have an equation sheet right here. That is that Gauss's law is the integral EdA is equal to the total charge inside divided by epsilon naught. Okay, good. So we've got part A down. Now looking at part B, they're looking now for the electric field outside. Okay, let's switch colors. I should have probably done that earlier. And let's go to maybe green. Okay, so we're going to go for part B. Did that show up? Not really. Okay, that's not good. Let me get like a different color. Okay. Does this show up? Blue? That's not really good either. Okay. Shoot. Oh, here's a blue one. Please work. Okay, that's thick enough. So B, we're going to ask for the electric field outside. So we're going to have a little, again, a Gaussian surface over here. There we go. That's the surface for the blue R, and where the blue R is greater than 0.2 meters. Yep. Okay. And it's really the same thing we just did with the change that this time when we do the integral EdA, the charge enclosed is not just Qi, but it's Qi and it is Qo. Okay, so these two charges together, but otherwise everything is the same. Okay, so we use the same expression here. I'll just write actually next to it right there. So this is for the previous expression we had. This one was for 0.1 meters, smaller r, smaller 0.2. Whoa, that's not very pretty, but it's good enough. That's for this one. And then for this one, we're going to go r is greater than 0.2 meters. And we can just write it down and say, well, E is equal to Qi plus Qo divided by 4 pi r squared. Wow, that's not really showing up great. So I'm going to just rewrite it in black on top of this to make sure it shows up nicely. E is equal to Qi plus Qo over 4 pi r squared. Okay, cool. So that works. We've got that down as well. Seems almost silly that they give that to us. And just for completeness sake, we could just also ask, well, what is E for R is smaller than 0.1 meters. Okay, and there we could also do a Gaussian surface and say we're going to do a Gaussian surface inside this sphere. Oh shit, sorry. Yes, thank you. Epsilon naught needs to be on here as well. So let's stick it there. Thanks, Hannah. So epsilon naught right there. Okay, good. Now we're complete? Yes. Okay, epsilon naught, there's epsilon naught there. Good. So how about inside the middle sphere, the spherical shell right there? If we are inside that, again, we could do a Gaussian surface, or we can just remember what we know. What do we know about metal objects? Inside the metal object, the electric field is 0. Okay, so we just write that down and say E is equal to 0. Okay, that makes sense. Good. So, good. Thanks, Hannah. Good. That's correct. Moving along now. So, now, so given what we actually have values for the voltages. Therefore, we should be able to find the charges on the two surfaces. Okay, because of course the charges are causing the potential. Okay, so if we take a look at both of these together, we can say, all right, we'd like to know the potential on the we'd like to know the charge in total of the two together. We'd like to know Qi plus Q0, Qo, sorry about that. And to do that, we can look at the potential. So we know that two things, V of infinity is equal to 0. We're given that. We're also given that V of 0.2 meters is a value, and that's specifically 100 volts. Okay, and we're also given that there's a relationship between E and V. Okay, and specifically, the relationship between E and V is that E is equal to minus dV dr. It's showing up. There we go. Okay. Oh shoot, I'm going to the bottom. Yes, good point. So there we go. There we go. Righty. I forgot about running out of space. That was not really smart. So, okay. And I might just erase in just a second. Why don't I just do that? I'm going to take parts A and B and erase them. And then it'll be a lot easier, I think, to deal with it. So I'm going to take a picture and I will upload that later. So go over here. Good, I got the picture. I'm going to quickly erase this. And that gives us some space to work. We still have the same diagram right there. I'm going to scooch this back up. There we go. There we go. Good. All righty. Good. So we're now in part C. Oh, crap. Sorry, I actually skipped the part. That was stupid. So we're going to get to part D in a minute. They're asking for the electric potential for R is greater than 0.2. That's actually a combination here. So they're asking for V of R for R greater than 0.2 meters. Okay, and the relationship I just wrote out is correct. There we go. And we can rewrite that equation in terms of integrals. We can say, okay, well, it's true that delta V is equal to minus the integral of E dr. There we go. Okay. And in our case, because the electric field is in the same direction as dr, we can drop that, and it's just going to be E dr. Okay? Makes sense? And now let's Okay, I'm going to just pause for a second because just that was a little fast and a little calculus-y, and I want to make sure you guys are with me. So far, so good? Okay, are you guys still there? Yes, Hannah is with us. So, okay, you guys okay with that? We're trying to find potential. Yeah, okay, good, good, thank you. And we know the electric field, and because electric field is the derivative of potential effectively, we can therefore integrate the electric field to get the potential difference, okay, between 2 points. All right, so let's figure that out. And specifically, we need to figure out from where to where we're going to go. So we're going to look at this and say, all right, we're going to go from here to infinity or from infinity come back. Either way is fine. It doesn't really make a difference which way we do it, which our beginning and what our end is. Okay? So let's say we begin our integral at, I don't know. In the solution, they begin at infinity. And I think that's maybe a little bit confusing to me, but fine. Okay. All right. So we're going to start at infinity. This is r equals infinity. And we're going to come back to some point which is a radius r away. R. Okay. So we're going to go all the way from here to there. And that's going to be our process. Okay. So that's going to be delta V is equal to, in this case, this is the final position. So this will be V of r minus V of infinity equals minus the integral from infinity to r of e dr. And I'm just going to write it like this for now to make sure we're okay with that for. Would it get rid of the minus then? The minus sign does not fall away. It's still there. You guys okay? Okay. You just yell if you have a question. So this thing right here, V of infinity is 0. Good. This is the thing we're looking for, V of r. So V of r equals minus, and here comes the integral from infinity to r, and now we're going to plug in for E what we found before. Now, what we found before was Qi plus Qo divided by 4 pi epsilon naught r squared, and then we have the dr. Well, no, I was just thinking if they had. Oh, I see what you're saying. So what it does is it flips the sign here. So we basically, if we did the integral the other way around, this would be V of infinity minus V of r. So in that sense, it does switch the sign here because doing the limits of integration upside down does flip the sign on the integral. Okay, integral from a to b is equal to minus integral from b to a. So that flips the sign. Okay, so what we have here, we've got a bunch of constants, and then we have the integral. Okay, so let's take a look. Minus integral infinity to r. Oh crap! Let's get the constants out first. Qi plus Qo. I'm going to be at the end of my board again pretty soon here. Qi plus Qo. Then we have 4 pi epsilon naught. Then we have the integral from infinity to r. Then we have 1 over r squared and dr. Okay? And I could have been a little bit more space savvy here, and then I wouldn't have to. Good. Okay, then I wouldn't have to. I have a little room here, so let's do that. So this is equal to, Good. The stuff out front still okay. Minus qi plus qo over 4 pi epsilon naught. And the integral of r to the minus 2, okay, just remembering what that is, r to the minus 2, you integrate that, you get r to the minus 1, and you pop a minus in front. So we get minus 1 over r. And we are integrating from infinity to r. Okay? All right, now we're actually losing the side of this. I'm bending this down a little bit so we can find it. Now we plug in infinity, we'll get 0. So it's going to be just whatever you plug in for r minus 0. Plug in r, you just get 1 over r. So our answer is qi plus qo divided by 4 pi epsilon naught times r equals v of r, and this is for r is greater than 0.2 meters. Okay, all good? Okay, so we found the potential for r greater than 0.2 meters given the total charge inside that position. And this is completely making sense because out here, out here, because at infinity, we've got 0 potential. Here we go. At infinity, we have 0 potential over here. That means anywhere in between, this should be just as if all this charge is concentrated at the center. So that result makes sense, and it's the same result that we would have expected under those circumstances. So it gets us through part C. And I'm taking a picture of this. This might not be the most efficient way of doing this, but we're getting something done, so that's good. Good. I got the picture. Okay. Everybody okay with that so far? Is this boring enough, or you want it more boring? Okay. All right, so let's take a look at part D. Now for part D, we can find that charge. Now, why can we find that charge? So just a reminder for how electric field and potential act, okay? So electric field can be discontinuous, okay? But potential cannot be discontinuous, meaning because we now know that V of R equals Qi plus Qo divided by 4 pi epsilon naught times R, and this is true for R greater than 0.2 meters, and because potential is continuous, meaning this is true for R greater than 0.2 meters, but it better also be true for R equals 0.2 meters. So we can put it like that and say, aha, we now know how to find the value for the potential at 0.2 meters. Reminder, electric field can be discontinuous, meaning it can be jumpy, because potential is continuous, but it's not guaranteed to be smooth. And the electric field is the derivative, minus the derivative of potential. So a continuous but not smooth potential can cause the electric field to be jumpy and therefore discontinuous. But potential will be always continuous. Okay? So that being the case, we can now plug 0.2 meters in here, and that means we can solve for Qi plus Qo because we know V of R at 0.2 meters is 100 volts. Okay, that's a given for us. So we have 100 there, okay? 100 volts. We have QI plus QO. And then we have, I'm going to do this. We know this is K, and this is going to make things a little easier. Might confuse you. If it does, sorry. So I'm going to use K here for 1 over 4 pi epsilon naught. K times QI, I like that better, divided by. I'm going to actually leave the units off too. There we go. The units are standard, so we're okay. So, all right. So multiply by 0.2. We get 20. We got K, which is 9 times 10 to the 9. And then we have the total charge. I'm just going to call it Q tote at this point. Okay. And that means now we've got Q tote, which is QI plus QO equals 20 divided by that number right there. And that's going to be in coulombs. So nicely done. 20 divided by 9 is 2.2. 2.2, and then that leaves the 10 to the 9, which is a billionth, which would be a nanocoulomb. Okay, so we get 2.2 nanocoulombs for the charge. Okay. Excellent. Now they come to part E, and in part E, we're going to actually sketch now the electric field, and in F, we're going to sketch the potential. Isn't that fun? I'm enjoying myself. You're enjoying yourself. I think this is a good problem to review potential and electric field. Okay, so we've got that result, and now we can figure out what to sketch this thing like. And I'm going to take another picture of this and then erase this to actually illustrate that. Hang on a second. Actually, I'm going to take a picture. I'm going to do this here. Boop. Boop. Okay, good. Okay. I'm going to erase that at this point. Okay, you guys been pretty quiet, so I'm just going to get a feedback here. Is this over challenging you, under challenging you, or the right amount? So too much, too little, or just right? Okay, good, excellent. So I know they're asking us to start with, good, excellent. They're asking us to start with electric field for part E. However, I have a feeling that we're going to be, well, we can maybe do both at the same time. I'm not sure. So part E asks for electric field, fine. Okay, let's do it this way. Yeah, let's do it this way. We can actually draw it like on this. That makes sense. So we draw it kind of, this is E, and this is R, and then we do the same thing underneath it for F. We also, so we can keep that kind of in mind, what it changes like for R and voltage. Okay, good. And yes, and now I made a little bit of a mistake because I didn't allow for negative values. So I'm going to put this in there. There we go. And then just pull this thing further down. Okay, and we're just going to remember that the most important rule about AP Physics and life is not to panic, and just to step through it, step at a time, and do what you know how to do. So we've got here, maybe this wasn't so smart. Okay. Anyway, yeah, I'm going to do it like this. Maybe not. Okay. So, okay, we are going to do it this way. Fine. Here's that part. And here's 0.2. We're just going to pretend that's 0.1. That's 0.2. 0.1, and that's 0.2. Okay, and this is in meters, and this is in meters. Okay, good. Now let's think about what we know. Okay, we already said earlier that the electric field all the way in the center is 0. So we can draw that in pretty easily. Say, okay, electric field inside this middle sphere is 0. And of course, if electric field is 0, potential is also 0. No. Okay? So if electric field is 0, that means that potential is constant inside. Well, if potential is constant on the inside, it must be the same value as it is at the surface, because it starts at 100, it is continuous. Okay, so we have at the inner sphere surface a potential of 100 volt, minus 100 volts. So that potential needs to be constant, needs to stay there. Okay. We also know that when we get to the outer surface, it needs to be 100 plus 100 volts. So that should be like there. Not sure why I switched colors there, but I did. Okay, and at that point, it's plus. We also know that in between, right? In between, this thing needs to drop off. Beyond, it needs to drop off. Okay, because that's the value we calculated just a second ago. All right. Now, how about the other stuff? So we got to get from down here to up here, and what shape is that going to be? And over here, what's going on with the electric field? Now, we do know that the electric field outside will be dropping off from some value to 0. Kind of like this shape, only it's dropping off 1 over r squared. So it's dropping off more rapidly, but the key thing is it comes from some value here, and then it drops off. Okay? That's how we're dealing with that. Okay? And we still have to go from below up there. So let's think about this for a second. So we have 0 electric field. And then if we go outside of this thing, right? Well, what kind of charge does this thing have? Well, it has a negative charge, right? It has a negative charge. And the outside has a positive charge. Makes sense? Okay, so we have a negative electric field in this here because it is indeed negative, and it will stay negative the whole time because it's pushing in that way. So we go from here to some higher value, a smaller value that's still negative. Okay, like that. Now, between those points, we have actually the electric. Did we get the electric field for part B? Oh, right. So okay, so the electric field between these points is behaving as if we're outside, as we are, a negative charge, okay? So it needs to be minus 1 over r squared, which would be a shape like this. So that's a shape like that. Okay, makes sense? Now, the only thing we have left here is the connection here. And for that thing right there, we have to have basically the same kind of shape because, again, the slope is decreasing. E is equal to dv dr. The slope, this is the slope of this, and that slope is decreasing, so it needs to kind of go like that. I don't know if that made sense. I hope that made sense because we're at the end at the 1500 mark, and we wanted to finish by 1500. So let's just quickly review, I hope, what we learned, or at least reviewed here today. They have exact values for the electric field. That was not asked in the in the rubric for you to be able to find the specific values for the electric field. But the important things to remember: V, continuous, not smooth. It could be smooth, but it doesn't have to be. Okay? And E can be discontinuous. And because this is not smooth, that causes the discontinuity, possible discontinuity of E. Okay? Because the derivative of V is E, minus derivative of dV dr is E. Therefore, this part right there, that's jumpy. You can see that, and that's going to be jumpy as well because the derivative is not defined at that point. Therefore, we have the jump here and the jump there because those are the not smooth parts for the potential. Okay, so we made it through the problem. I think it's a good review of Gauss's law, of electric field and potential graphs. So that's why I selected it as a problem that I think would be good to work through. And I hope you learned something from it, got you guys going on the review. We needed to kind of talk about next steps because we are preparing for a closure. That's at least the plan for now, April 20th. It does not reach zero because the electric field here, this electric field, is caused by the charge inside it. And it's a negative charge. And the electric field by that negative charge is minus Q divided by 4 pi epsilon r squared. So it's a negative r squared, so it'll look like this coming down, although it does not go beyond this point. And up here, obviously, that doesn't happen either because then this charge kicks in. But that's why it's still at that point not zero electric field. The electric field is still pointing in this direction. So we make a drawing here. That's the electric field everywhere. And as you can see, because the electric field lines are getting tighter together as you get closer to the 0.1 meter surface, then you get a stronger by magnitude electric field as you get closer to the 0.1 meter surface. Okay, is that making sense? All right. Okay, next, plans. What would you guys like to do? I am happy to meet with you as often as you want to. We can meet during all our periods. We can meet through every second period. We can meet also Wednesdays. I don't know what you guys would prefer to do. We don't have to make a decision right now for the entire next 2 weeks, but tell me when you want to meet again. Do you want to meet again tomorrow? Normally we would have class. Okay. Do you want to meet tomorrow during our regular class time, which would be, we have to meet during regular class time. That would be 5th period. Okay. Do another free response, kind of like what we did today. Tomorrow, 5th period. So that would be 11:30 to 12:15. I'll come anytime. Okay. Okay. Does it sound good? Tomorrow? Meet tomorrow? Yes. 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 Okay. So we will meet again tomorrow, 11:30 to 12:15. And good. Yes. We are going to do a circuits problem tomorrow. Okay. This was an electrostatics problem, and we'll do a circuits problem tomorrow. Yes, we were reviewing E&M until the closure, and after that, we're going to do mechanics. That's correct. Yep. Yes, yes, yes. Okay, good. I will see you guys then tomorrow. I will post this on, well, on YouTube, obviously, and then it's recorded. Yes, we were going to do, I'm going to do problem 2 tomorrow, that is a circuits problem. It's basically a current, a resistance, and those kind of things. And I think it'd be a good practice problem. Okay, so we'll do problem 2 from this free response tomorrow at 11:30. Okay? All righty. I'll post the pictures and I'll post this video and I'll see you guys tomorrow.